In previous segments, we learned a little bit about chemical bonding. We looked at first ionic bonds, where oppositely charged particles are attracted, and then covalent bonds. In a covalent bond, the outer electrons are shared between the bonding atoms. We looked at both non-polar covalent bonds and polar covalent bonds. There is another type of bond. It's not really a formal bond, but we call this a hydrogen bond. And a hydrogen bond is a weak attraction between neighboring polar molecules. So we need to remember that polar covalent bond concept and the fact that we create polar molecules that have some charge separation. Now, really, hydrogen bonds can occur within a single molecule if that is a very, very large molecule, but generally it occurs between neighboring molecules. We have an example here of hydrogen bonding. These represent water molecules, H2O. So we looked at water previously when we were discussing polar covalent bonds and the formation of polar molecules. So you can see here on this water molecule right in the middle, we have the partial positive charge on hydrogens. We have a partial negative charge on the oxygen. Now each of these dotted lines between all of these neighboring water molecules represent a hydrogen bond. It's a weak attraction between the negative pole of one water molecule, that's where the oxygen would be, and that's going to be attracted to the partial positive pole or a hydrogen atom on a neighboring molecule. So again, each of these little dotted lines represents a hydrogen bond. These are very, very weak, but there's just so many of them, and they're very, very important in biological systems. Water is a very polar molecule because of the polar covalent bond, and the polar covalent bonds allow these hydrogen bonds between neighboring molecules. We need to discuss water and some very important characteristics of water, and the fact that it is a small, bent, polar molecule that participates in these hydrogen bonds is responsible for the special properties of water that we'll be discussing next. Water is the most abundant compound in living organisms. We're over 90% water. It's vital to life as we understand life. Water is very polar. We just discussed that once again. Polar or ionic molecules will dissolve in water. So any other molecule that's polar or an ion like a salt will dissolve in water. A couple of terms that we need to be familiar with are hydrophilic. Hydro means water. Philic means to love. So we would also call polar or ionic molecules hydrophilic molecules. They will dissolve in water. What we see here in this picture is an example of salt, sodium chloride. That's an ionic compound. So we saw earlier how we form the sodium ion. When sodium loses an electron, becomes a positive ion. Chlorine will gain an electron, becomes a negative chloride ion. Those come together in the formation of the ionic compound sodium chloride. Well, salt will dissolve in water. And so what we see illustrated in this diagram is how the water molecules orient themselves around these different ions. So on the left, sodium, that's positive. And if you look at the three water molecules that are surrounding sodium, it's the oxygen of those molecules that's interacting or surrounding that sodium, and that is because the oxygens all have that partial negative charge. If you look over at chlorine, or the chloride rather, is a negative ion, and so the water molecules surround that chloride ion and they orient themselves in such a way that the partially positive hydrogen is surrounding that chloride. And that allows these ionic molecules to dissociate, to separate, to dissolve in water. Anything that is ionic or polar will dissolve in water because water itself is polar. The term hydrophobic, hydro means water, phobic means to fear. Anything that will not mix with water we would call hydrophobic. This is going to be primarily non-polar or non-ionic compounds. Some other characteristics of water that we'll discuss, and again keep in mind most of these are a result of the fact that water is a small polar molecule that participates in hydrogen bonding. And water is a liquid at room temperature. Most small nonpolar molecules, we saw an example of a small nonpolar molecule earlier, that was methane. Methane is a gas at room temperature, and it is a gas because there is no hydrogen bonding, there is no attraction that keeps those molecules stuck together. Water, on the other hand, is highly polar, participates in all of the hydrogen bonding, and so that keeps those molecules very close together, and so at room temperature it would be a liquid rather than a gas. We say that water is the universal solvent for polar molecules, also ionic molecules. We just looked at that a moment ago. Water molecules are cohesive. That means they stick together. They're hydrogen bonded. They have that attraction to one another that makes them liquid at room temperature. They are also adhesive, which means they will stick to other molecules, especially other polar molecules, because we can have the hydrogen bonding. Water has a high surface tension. Again, all of these are related. The water molecules at the top of a container or even just a film of water are attracted to the water molecules below them. And so that creates what we call the surface tension of water. Okay. These next two are also related. Water has a high heat capacity. This means that water can absorb a lot of energy without changing temperature. Because that energy can be absorbed in the hydrogen bonds between the neighboring water molecules. Water also has a high heat of vaporization. The heat of vaporization is the temperature, the amount of energy that needs to be put into that to cause it to change phases, to go from a liquid to a gas. So for water to boil or turn to a gas, enough energy has to be put into that solution so that those water molecules on the surface can break free from their neighbors. Those hydrogen bonds have to be broken in order for individual water molecules to break free and become a gas. The last one, water molecules participate in most biological reactions. In the next units here from Chapter 2, we're going to start looking at some biological reactions and building some larger molecules. And we'll see that in many cases, water is a participant in those biological reactions. The last topic in this segment is acids and bases. This is many times one of the more difficult concepts for students. An acid is something that will dissociate in water. That means it's going to come apart. And when it comes apart, it releases a proton. Now, I use this symbol there, H+, to represent a proton. H+ is a hydrogen nucleus. If you remember, the atomic number of hydrogen is 1. It has 1 proton and 1 electron. If you take the electron away, what's left? A proton. And so many times we will use the H+ to represent a proton. Or a hydrogen nucleus. So an acid is something that's going to dissolve in water, and in doing so, it releases a proton, so we call acids proton donors. An example of this you see in the diagram is hydrochloric acid. If you put hydrochloric acid, HCl, into water, the hydrogen ion, or proton, and that chloride ion will dissociate, and so that is going to release free proton into that solution. And in doing so, it increases the proton concentration of that solution. Down at the bottom, we see the H plus that represents proton. Whenever we put brackets around it, that means the concentration of the proton. And so acids will increase proton concentration. We call them proton donors. So we're going to begin talking about pH, and in just a moment we'll see the pH scale. And the pH scale is comparing different solutions to pure water. So a solution that has a higher proton concentration than pure water would be called an acidic solution. Whenever we put that on the pH scale in just a moment, acidic solutions have a lower pH number. A base is going to be something that will either take up proton or it can release a hydroxide ion, an OH. Even if it releases a hydroxide ion into the solution, that hydroxide ion then will take up a hydrogen to form water. So we call bases a proton acceptor. Now in our diagram here, our example is sodium hydroxide, NaOH. If we add sodium hydroxide to water, the sodium and the hydroxide ion will dissociate. That OH is going to pick up any free proton in the solution and it's going to form water, H2O. And so this is going to lower the proton concentration of the solution. So if we compare this again to pure water, a solution with a lower proton concentration than pure water is called a basic solution or alkaline. And whenever we look at our pH scale, basic solutions have a higher pH value, pH number. Okay, I mentioned that the whole pH scale is based on pure water and the concept that's called dissociation of water. So if we have water, H2O, H2O is constantly breaking apart and then reforming. So we have arrows going in both directions here. That represents the fact that this reaction goes back and forth very, very rapidly. But at any instant, if we were to look at the molecules in pure water, at any instant, a number of those are going to be broken apart. Remember, oxygen is one of those very electronegative things. It likes to steal electrons, and so that's what happens. The oxygen steals the electron away from the hydrogen. It just, for an instant, breaks that bond, and so we have the hydrogen nucleus, which is the proton, and our hydroxide ion. And then these come back together, break apart very, very, very rapidly. At any instant, there is 10 to the minus 7th moles of water that is dissociated in water. And so our pH scale is based on that value. So remember, whenever we are assigning a pH value to anything, we are comparing its proton concentration to that of pure water. So we use this value, the dissociation of water, to make our pH scale. The pH scale is 0 through 14. A neutral pH is 7, and so pure water is neutral. It is assigned a pH value of 7. Anything less than 7 would be acidic. It's going to have more proton than that is found in pure water. Anything that has a pH value greater than 7 would be a basic solution, and it's going to have a lower proton concentration than water. So you can see some of the things here. Pure water is at 7, tears and saliva are right around 7. Urine is usually a little bit acidic. It's about 6. The coffee that we drink in the morning is typically rather acidic, has a pH of around 5. Soda is very acidic. Look at stomach acid way down here. The pH of stomach acid is down between 1 and 2. Very, very acidic. Some basic things. baking soda, stomach antacids have a high pH. They are basic. Ammonias, oven cleaners, some other things that are shown here that are very, very basic. The last thing we'll mention here is buffers. A buffer is something that can be added to a solution, and it's going to stabilize the pH of that solution. And so the solution will resist pH change. These different chemicals that act as buffers can either take up proton. So if the solution gets too acidic and there's too much proton, these chemicals will grab up that free proton. Or if the solution gets too basic, it will take up hydroxide ion. Okay? The pH of many body fluids, blood for example, has to be maintained within a very, very narrow range. This is an excellent example of homeostasis. We have to keep blood pH within a very narrow range. There are several systems that act as buffers to stabilize the pH of blood. There are some specific reactions involving carbon dioxide and carbonic acid, which is the primary buffering system in blood. And we will look at these in much more detail whenever we get to the lessons on the respiratory system and the urinary system, which are extremely important in controlling blood pH.